What drives time? What makes time dynamic? What causes a present moment, as soon as it appears, to be immediately replaced by another, which itself will disappear? What drives this renewal? Physicists answer, we don't know. This world we live in and to which we are adapted deceives us about the universe. It makes us believe that phenomena are governed by laws that resemble them.
Hello everyone, welcome to this new episode. Today our guest is Étienne Klein, with whom we'll be talking in particular about time. So, time, there are a lot of common expressions like wasting time, having time, as if time were an object, as if it were something we could possess, something we could almost touch. And yet, when we try to define time, we often struggle to find the words to describe it. Comment est-ce qu'on pourrait définir le...
Quite a few people have tried to do so. But every time we try to define time, we assume in the definition that it exists, and we define it in relation to itself, which is the opposite of a real definition. In other words, if we wanted to define time, we would have to relate it to concepts that are more fundamental than itself. And it's not certain that any such concepts exist. In fact, there's a very good remark by Paul Valéry who says that, in the end, if we understand each other when we talk about time, it's because we speak quickly. In other words, it's the sentence we insert the word time into that determines what time means in that sentence. And he says that if we take the word time out of the flow of speech we've inserted it into and strip it of its context, then it becomes a mystery. We wonder if it's a physical entity, a fluid, a kind of river, if it's a product of consciousness, if it's something produced by culture, and so on. And so there you have it. It's a question that remains, in my opinion, unanswered. Time, in a certain way, imposes itself on us without us being able to say exactly what it consists of. And there have been all sorts of attempts made by philosophers, by physicists, by linguists, and by others as well to try to grasp it. And when we look at the work that has been done, we feel like turning first to the philosophers, because they were the ones who first began to ask the question of time. And when we do that, we realize, first of all, that they do not agree with each other. And so, there are several theories that coexist, so which one will you give credence to? To the one who talks about time in a way that matches what you think? Or will you choose a philosopher who is an authority, who has made history, Kant or Searle, Heidegger or another? And above all, when you look at the different doctrines of time developed by philosophers, you realize that they can be divided into two categories. There are those who make time dependent on consciousness, and there are those who consider that time is independent of the subject's consciousness, and those who make time dependent on consciousness are, I believe, the most numerous. There are Saint Augustine, Kant, Searle, Heidegger, Merleau-Ponty, Bergson, with this idea that it is we who temporalize the universe, actually. Our consciousness of time projects onto the universe, onto phenomena, a succession that they do not have in themselves. These philosophies, we call them correlationist philosophies, they correlate time to the consciousness we have of it. But they have to face a terrible paradox, which is called the paradox of ancestrality. By the fact that we have learned, essentially in the 20th century, that the universe is at least 13.7 billion years old, that Homo and its consciousness have existed just a few million years. And when we put these two numbers together, the obvious conclusion is that the universe has spent most of its time without us. But if it needs us in order to pass, how could it have passed before we appeared? If time depends on the subject, and if the subject appeared within time, how could time have passed before the subject that makes it pass came into being? And this paradox of ancestrality, many consider it serious enough to conclude that time is independent of consciousness. It's a physical identity we're used to, since at school we learn to represent it with the parameter little t, and we even draw the time axis. But when we draw the time axis automatically, without realizing it, we do something terrible, because we draw the flow of time as if it was space. Yet, there is still a difference between time and space. It's that the different points that make up a segment in space, they exist together, they coexist. A length consists of points existing simultaneously. But when you draw the time axis as a segment, it's made up of a succession of instants that, by definition, do not exist together.
All right.
And here there's a little shortcut. By the way, when Bergson and Einstein met in Paris in 1921, Bergson's main question was about that. You physicists treat time as if it were space, but it is necessarily of a different nature than space. And to say that time moves forward, in other words, that we can't remain in the same present moment over time, we add a little arrow. But what is the driving force of time? What is it that creates a dynamic in time? What makes it so that a present moment, as soon as it appears, is immediately replaced by another one which, in turn, will disappear, and so on? What is the engine behind this renewal? Physicists answer, we don't know, okay? We draw an arrow to show it moves forward, but can't say what causes it. And then this arrow, well, not this arrow, sorry, this segment, raises some deep questions. When you are present at moment t, the present moment, do the moments of the future already exist, just waiting for you to arrive? And are the moments of the past still there, in places where you no longer are? Or should we think of the present moment as being surrounded by nothingness? Since we're speaking now, the future doesn't exist. It will only become real when it becomes present, that is, when it ceases to be the future. Yes, we can have fun like this for a long time. To sum up, if you say that time depends on consciousness, and a lot of everyday language expressions suggest that, you have to face the paradox of ancestrality that I summarized. If you say it doesn't depend on consciousness, you have to face the problem of what drives time. What makes it move forward? What makes each moment give way to another moment that has the same status? There you go. That's a nice program.
That's quite a program. Especially since just before we were talking about how time passes. The simple fact that time passes implies that it passes in relation to something, that it passes within something.
I'm not sure time passes. Indeed, as you say, to speak of a flow, and that obviously comes from the metaphor of a river flows in a bed with banks that do not flow. In other words, to speak of flow, you have to conceive of what does not flow. So, if you say that time flows, you have to say what it flows in. To discuss the flow of time is to consider something outside time. What is it made of? So, maybe we'll talk about the theory of relativity, which gives some foundation to this idea. But when we say that time flows, even though it passes, we need to question the fact that it never stops passing as it passes. All the better, what actually passes are the moments. Moments pass because they are constantly renewed, driven by the engine of time, which itself does not pass. In other words, the engine of time never stops making the moments pass. And so this engine does not pass.
To come back to this engine, there's still the peculiarity that it turns more or less quickly depending on certain properties. I'm thinking about the theory of relativity, so depending on the mass, depending on the speed. How can we reconcile that with a coherent view of what time is?
Listen, that's a subject that concerns me because indeed we talk about time as if it had a speed. A speed that depends on the speed of the observer in space, to take the example of special relativity. But how do you define the speed of time? Remember, speed is the derivative with respect to time. The speed of a car is the distance it travels over a given period of time. You divide a length by a time, a duration. In the case of time, what is the speed?
Yes.
That doesn't make sense. Saying that time has a speed would mean that it changes its flow rate compared to its own flow rate. It's a tautology, it doesn't make sense. The only way to talk about the speed of time is to say that it moves forward by 24 hours every 24 hours. You're not getting anywhere, okay? So there's no speed of time. And by the way, one of the problems with popularization is that we've tried, at least in France, to present Einstein's theory of relativity as if it were an evolution and not a revolution. And we said, in the end, time and space are like they were for Newton, except that the speed at which time flows depends on the observer's speed in space. That's a sentence you still read in high school textbooks in philosophy classes. The speed at which time flows depends on the observer's speed in space. First, I don't know what the speed at which time flows means. How do students understand this sentence? They say to themselves, in the end, we're both in the same room. We can use our watches to time how long it takes us to read a book. It takes us 2 hours to read a book. And then imagine that you, or rather me, okay, I'll sacrifice myself. I leave in a spaceship at a speed that is, I don't know, half the speed of light. I take with me books of the same size. I take my watch and I tell myself, because I've read it, the speed at which time passes depends on the speed of the observer in space. All right, so I leave in the rocket. I'm traveling through space. We agree? Yes. So time must move at a different speed for me. Well, no, I do the experiment. I read a book of the same length with my watch. And in the rocket, I measure that it took me 2 hours, just like here, to read the book. In fact, the theory of relativity is called relativity because it is based on Galileo's principle of relativity, which says that motion is as if it were nothing. So when you are moving in space, everything happens as if you were not moving. You can't move relative to yourself. Yes, all right? So there you go. When you're in the rocket is a frame of reference equivalent to this studio, so everything happens as if you were here. The difference between Galileo and Einstein, from this point of view, is that when I come back from my trip, which will last, according to my watch, I don't know, 2 years, when I come back here, you will be dead. Not because you will have a shorter life than mine, but because my time will be out of sync with yours. When you read what Einstein says, it's not at all that there's a universal time whose flow rate depends on the speed of the observer in space. He says that there are as many proper times as there are different frames of reference, or different observers. So I have my own proper time, you have your own proper time. We were both on time for the meeting we set for today, because our proper times are synchronized. And why are they synchronized? Because our speeds of movement in our world are negligible compared to the speed of light. I came by car, you came, I don't know how, maybe between the time we made the appointment and today you took a train, maybe a plane, and yet our watches stayed synchronized. Why? Because our speeds of movement, even by plane, are negligible compared to the speed of light. But if we could travel at speeds that are not negligible compared to the speed of light, for example, half the speed of light, we wouldn't be able to make appointments. Our proper times would become unsynchronized so that our respective watches wouldn't agree on the time of our appointment.
Is it possible to go back in time?
No.
We're sure about that.
First, what does it mean to go back in time? It's 2025. What time do you want to go back to?
To 1800.
So before your parents were born, yes. Okay, but maybe you'll do it there. First, can you handle it mentally? When you go back to the past, do you know what happens in history between 1800 and 2025? Or are you, like the people of that time, unaware of what happens next? Yes, first of all, it's not the same experience. If you know the rest of history, you could never stand to live in 1800. Would you visit a dentist in 1800? Are you sure you'd have the courage to go to the dentist in 1800 or have surgery, knowing that today you can have surgery under anesthesia? You wouldn't be able to stand the conditions back then if you know that later on they were improved. Then, in physics, there's a very fundamental principle called the principle of causality. It's a principle that basically says, historically, every event has a cause that comes before it. Every event ultimately is the effect of a cause that preceded it. So there's a required sequence between the cause, which comes first, and the effects it produces. This principle of causality even in classical physics, requires that time cannot form a loop. Imagine time is cyclical, so it forms loops. There is a cause A that occurs here, at point A, which produces an effect B. A little later, and by going into the future of the effect, you return to the past of the cause, so the effect can cancel out the cause that produced it. And imagine by going back in time to 1800, you could prevent your parents from meeting. That's troublesome for you. To avoid family disruptions, time was described as linear. Linear doesn't mean it goes in a straight line. It means that every moment that happens is a brand new moment. And time can't pass through the same moment twice. So saying that time is linear and not cyclical is already a constraint imposed by the principle of. As you certainly know, the principle of causality will face all sorts of complications, especially with quantum mechanics and also with thermodynamics. And so in the end we have finalement dissolved the notion of cause into the notion of law. We don't say that bodies fall because of their weight. We say that there is a law of gravitation.
Right.
And finally, the modern version of the principle of causality has freed itself from the idea of cause. It simply says if an event has occurred, it will remain eternally true that it has occurred. In other words, you cannot later undo the truth of an event that has happened. Even if there are no witnesses, even if history is falsified, even if the event in question left no trace, it happened. So actually the principle of causality is simply a principle that protects any event that has happened from feedback coming from the future. And what's extraordinary is that this principle of causality, stripped of the idea of cause, has been extremely restrictive in the way physical theories are structured. For example, in Einstein's case, with special relativity, he says that a particle of matter cannot go faster than light. There are things that go faster than light. For example, I can cut paper at a speed greater than that of light. The intersection of two lines, which are the two blades of a pair of scissors, can move faster than light in principle, but there is no transport of matter. So it doesn't contradict Einstein's principle of causality. But a particle moving through space cannot do so faster than light. And you see that the principle of causality in this case is expressed as a prohibition. A particle is not allowed to go faster than light, but a prohibition can be violated. So we can imagine that one day we'll find a particle, but where the principle of causality gained strength was in the late 1920s, when a physicist named Paul Dirac tried to find equations that unify quantum mechanics and special relativity to describe the particles of cosmic radiation that move very fast and are also quantum particles. So you have to combine quantum physics, which describes small objects, and relativity, which describes fast objects. Combine the two. And Dirac, I'll keep it brief for you. It's a fascinating story, but I'll give you the full summary. He writes an equation, and he realizes that this equation, if we wanted to respect the principle of causality, implies the existence of what we call antiparticles. He predicted that every particle must have an associated antiparticle with the same mass, opposite electric charge, and so on. And it turns out that antiparticles were discovered. And so antiparticles, their existence proves the principle of causality, and therefore the impossibility of traveling in one's own time, in one's proper time. Because, as I said earlier, I can travel into the future by moving through space, but I can't travel through my own proper time. You see, it's subtle, but it's important to make. We hear a lot of things about that.
Earlier we said that time can't pass through the same place twice.
At the same instant.
At the same instant. Does that mean that each moment can never happen again? Which means that, in fact, the universe is moving in a specific direction? I'm not sure if my question is clear.
Yes, it means that there is a flow of time. There is a flow of time. The flow of time is the fact that this little arrow associated with the engine constantly renews the present moments without ever repeating the same one. So all the moments have the same physical status, but they are all different. Notice something amazing. When you write t in an equation, t does not depend on time. That is to say, time does not change over time in how it functions. When you write a physics equation that has t, the equation is the same for all moments in time. So the fact that time does not depend on time in the equations of physics means that the equations of physics, the physical laws, are invariant under time translation. In other words, the universe evolves, but it doesn't evolve by changing its laws. That created a lot of confusion in the 20th century. Einstein got involved and so on. And what we eventually understood is that when we say the universe evolves, what we mean is that the physical conditions evolve, temperature, density, and so on. But the physical laws that make it evolve, in principle, do not evolve. They are invariant under time translation. By physical laws, I mean the actual ones. I'm not referring to the laws of physics found in books, which do change. Newton's laws differ from Einstein's. So there is a history of the laws of physics. We believe physical laws have no history. They're always the same. And that's what we use to understand its history. When we collide protons or particles at CERN in Geneva at very high energy, we recreate the physical conditions of the primordial universe. Very high temperature, very high energy density. And since the laws today are the same as they were back then, we see today the physical phenomena that took place in the distant past. That's how we found the Higgs boson and so on. So you see, it's not a journey through time. It's a return to youth. We give the universe the chance to relive, here at CERN in Geneva, the physical conditions it experienced in the primordial universe. And we can do that because the laws of physics don't change as time goes by.
By the way, if I go back in time...
You can't.
If I project myself into a very distant past...
With imagination, you do whatever you want. And your body is not going to go there. It's not going to follow you.
If we mentally project ourselves into a very distant past, at the very beginning of the universe, even the moment before the beginning of the universe, if that even makes sense, before time zero, there were no events. There was no succession of events. Can we say there was a time before the Big Bang?
That depends on what you call the Big Bang. Because actually we're talking about the Big Bang the way we talked about it in 1950. In other words, we say the universe is expanding. We have Einstein's equations. If we extrapolate them back as far as possible, we end up with a universe that gets smaller and smaller, hotter and hotter, so it's contracting. And then we reach a point that we call a singularity. A universe of zero size, a single point, and we associate this thing with time zero. And we say that's the Big Bang. And indeed, it raises the questions you're asking. What was there before? What acted as the cosmic match? What set things off? Was there a time before? Very well, except that between 1950 and today, things have happened. When you make the extrapolation I just mentioned, it's based on Einstein's equations of gravitation, which is the dominant force on a large scale. So it's the one that actually allows us to extrapolate into the past. But as you know, Einstein's equations only describe gravitation. But in the universe, there are other forces. Electromagnetic forces, nuclear forces. All right? So when you make this extrapolation, there comes a point where the physical conditions, the temperature, the energy of the particles are such that you have to take the other forces into account. Not just gravity, but the other forces are described by quantum physics, which is not the same theory as Einstein's. So there comes a point when you extrapolate back into the past where your mathematical calculations become incorrect. Physically. They may be mathematically correct, but they become physically incorrect. They don't describe all the processes that the particles undergo from a certain point in history. And that moment is what we call the Planck time, or the Planck wall, which is the moment in the history of the universe before which, in order to say what happened, you have to combine quantum physics and general relativity. So today we should say there's the Planck time, which is not the origin of the universe, which is not the beginning. And since the Planck time, this and that have happened. But before the Planck time, we don't know. We can try to find out. Pour tenter de le savoir, we have to combine quantum physics and general relativity. For 40 years, there have been people working on this, trying to unify the interactions in order to have a mathematical formalism that would allow us to describe the universe before the Planck time. You've heard about string theory, loop quantum gravity, twistor theory, and so on. There are plenty of theoretical approaches. But the fundamental point is that, I'll give an example before I say it. Let's take string theory as an example. It describes particles as strings that exist in a space-time with more than 4 dimensions. But above all, it says that there must be a maximum temperature in the universe. Limite. Because at every point in space and at every moment in time, the temperature in the universe could not have exceeded a certain value, which is very high, but still finite. Just by saying that, the zero moment of the old Big Bang models takes a hit. Why? It was linked to infinite temperature. String theory claims this infinite temperature never occurred. So this zero moment is a fiction. What does string theory say when we apply it to what came before the Planck wall? It says there was a previous universe that was contracting, that was heating up. It reaches the maximum temperature allowed by the theory. At that point, it can't contract further, as that would increase its temperature. So it bounces back. And so the Big Bang is no longer a singularity with a beginning that we associate with time zero. It's a phase transition between the universe before and the universe after. That's one example. You might tell me that string theory is wrong. It probably is. The conclusion is wrong because it's based on a theory that isn't the right one. The important point is that no matter which theory you choose to combine quantum physics and general relativity, and to become able to describe what happened before the Planck wall, the initial singularity disappears. What does that mean? It means that we don't have proof that the universe has an origin. And we don't have proof that it didn't have one either. Okay? So it's an open question. By the way, just a side note, what is the meaning of the word origin? If I ask you about your origin, you'll tell me about your parents, your grandparents, maybe the country you come from. In short, you're going to tell me a story in which you are not present, but one that culminates in you. So the word origin in common language means conclusion. To speak of the origin of something is to tell the story of which that thing is the conclusion. So we can absolutely describe the origin of atoms. For example, by explaining the nuclear reactions that took place in stars and culminated in atoms. And that works very well. But if the question that interests you is not the origin of things that are in the universe, but the origin of the universe itself, you will have to tell, using the same method, the story of what happened before the origin of the universe, of which the origin of the universe is the conclusion. If you talk about the universe's origin, you mean there's no story before it? It's an absolute origin, not an unfolding genealogy? So let's be wary of all those who tell us the origin of the universe by saying in the beginning there was this or that. So this or that, it could be a primordial ocean, primitive chaos, the word, whatever you want. You see that it doesn't work. Or this thing that you say comes before all the others has always been there. So there has always been something. If something has always existed, the universe has no origin. Or maybe that thing hasn't always been there. That means it's the result of something else that came before it. So it's not the origin. So when you name the origin of the universe, you're saying something that contradicts the idea that the universe has an origin.
Another question I have, earlier we talked about time and associated it with the succession of events.
Instant. No event. Because precisely, except in general relativity, time is independent of events. Take Newton, for example. What happens in time doesn't change it. The parameter t, whatever happens, is not affected by what happens. So time is the succession of instants. And the big question is, how is it connected or not to events? Current. We keep associating them. We don't hesitate to attribute qualifiers to time. We say there is physical time, geological time, psychological time, biological time. We invent as many kinds of time as there are different temporalities. I agree that some biological phenomena have their own temporalities. We measure them with physical time. In other words, it's a kind of misuse of language to say that time resembles the temporal phenomenon. Besides, if time resembled the temporal phenomenon, that is, if it had some kind of harlequin costume that changed every time a certain type of thing unfolded within it, it would no longer be a concept. We wouldn't be talking about time, we'd be talking about temporality. And by the way, in language, the word time that we were talking about earlier with Paul Valéry, you can do a funny exercise. You record every sentence you've seen or heard with the word time. And you ask, but in this sentence, what is the meaning of the word time? You'll notice some sentences use the word time to mean duration. Duration. It's not the same thing as time. Time makes duration, but they're not the same. Duration is not the same thing as time. There are sentences where the word time will mean causality. Sentences where it will mean simultaneity, succession, change, becoming, speed, etc. That's too many meanings for one word. Okay? So the big question is, from what point of view could we do a critical analysis of language? What Paul Valéry called a cleanup of the verbal situation. How do we clean up language so that it talks about time while taking into account what we know about it? And that's not easy. With a colleague named Vincent Bonton, we organized a conference in 2022 in Cerisy. We invited physicists, biologists, mathematicians, cosmologists, psychoanalysts, historians, philosophers. We asked them to give the same talk as usual, but without using the word time, or when they used it, to say why they used it and not another word. Every time they used it, they lost a point. They had 20 points. Few finished their presentation with points remaining. It's automatic. You say the word time and it comes to mind because the language has carried it for so long. Without thinking about it, we talk about time without questioning the meaning we give to that word. But well, since physics became very powerful from the moment we mathematized time with Newton, we concluded that in the end, it's the physicists who have control over time. Conceptualizing that made physics so effective. We were able to predict kinds of planets, the Higgs boson, gravitational waves. All these discoveries relate to how physics represents time. But the problem is that when Newton says time, it's T or T, it's time, he doesn't say by what intellectual strategy. He recognized in this mathematical parameter the thing we call time, which we discuss differently, and the status of the parameter T would require us to talk about it. In other words, what is the mechanism that made him recognize time in that thing? Because the parameter T doesn't match our description of time. It doesn't change over time. It has nothing to do with change. It's not affected by temporal phenomena. It has no speed, in short. It doesn't look like what we think of as time. So let's do a thought experiment. Let's imagine that Newton called the parameter T by another name. He called it thing. Physicists would hold conferences about thing, while linguists, biologists, and others would hold conferences about time. Yeah?
The difficulty is that the word time is highly polysemous.
That's the problem.
It has as many meanings as we have uses for it.
Look, there are people who say that when nothing happens anymore, time stops. Some say time stops, but what does that mean? There are some who say, but on the contrary, when everything stops, time itself keeps passing. When a physical system reaches equilibrium, nothing much seems to happen anymore, and time keeps passing. So that creates all kinds of confusion. And actually, indeed, when we talk about time, we make statements that contradict each other.
Now, we're coming to the end of our interview. This is also the part of the interview where I ask about reading recommendations. I know you're writing a book. I don't know if it's been published yet. It has been published, yes. So, what is this book about?
It's called Physical Transports, plural. It was just published by Gallimard. I don't have time to summarize it because it talks about too many things, but I can give you the gist. I learned, thanks to a fellow conductor, that Maurice Ravel, the composer, who was apparently a bad conductor according to what people say, once conducted an orchestra during a concert where they were playing his works. And in the middle of a piece, suddenly he stopped conducting, as they say. Incredible. That caused a cacophony in the orchestra. Some musicians stopped playing, others played at their own pace, and then after a while, he started conducting again. Another cacophony. And at the end of the concert, they asked him, "Maestro, what happened?" And Ravel replied that for a short moment, he heard in his head an inner music, or rather, a different possible interpretation of his work from the one the orchestra was playing. Yet his inner music made him deaf to the music around him. I thought to myself, that's the human condition. Not that we're locked inside ourselves, but we're locked inside the world. What I call the world is the earth, the atmosphere, the sky as we see it from Earth. We're not in a vacuum. In short, we're in a very particular place in the universe. And this world in which we live and to which we are adapted misleads us about the universe. It makes us believe that phenomena are governed by laws that resemble them. For example, if I drop objects of different masses, I see them fall at different speeds. But in a vacuum, that's not true. The one who understood this was Galileo. And Galileo, in 1664, when he stated the law of falling bodies, that all bodies fall at the same speed in a vacuum, he said this at a time when people didn't know how to create a vacuum. It's impossible to carry out an experiment with bodies falling in a vacuum. And on top of that, people thought that a vacuum couldn't exist. The big question is, how did he find the right law when that law contradicts what we see? And so that's the starting point of the book. It's the idea that actually we're trapped in the world, but we can still find intellectual ways to get out of it through thought, to find universal laws that being found allow us to return to the world to understand what's happening. That's why the physical laws we learn at school and even afterwards are laws that contradict observation. They're not deduced from observation. The principle of Galilean relativity, which I mentioned earlier, says that motion is as if it were nothing, and you wonder why you pay for your train tickets. If motion is like nothing, it is free. Or the principle of inertia, a body that is not subjected to any force, moves in a straight line at a constant speed. But when you're riding a bike, you can see that's not how it works. For the bike to move, you have to apply a force by pedaling. So the real physical laws are laws that are paradoxical because they contradict the experience we have of movement. And then we have to understand how laws that contradict what we see still explain what we see. In the case of the bicycle, you pedal, and that makes your bicycle move forward. If you stop pedaling, the bicycle, if there is no friction from the wheels, no air resistance, and if the ground is flat, you could keep going in a straight line at a constant speed. But we are not in a vacuum, there is friction. So we are slowed down by forces that oppose the movement. We don't directly observe the principle of inertia. It's kind of disguised by the very specific conditions that we have in this world. In fact, Earth is a very special place. Take the sky, for example. The Greeks observed it. All civilizations have looked at the sky as it appears. The cosmos, orderly, stable, with fixed stars. Look at the Greeks, the starry sky, the Milky Way. It's the framework that underpins thought. It's a model for thinking. But that's simply because we can't see much. If we had particle detectors like the ones we have today, we would see that the sky is full of violent activity. It's very violent. Very, very violent. There are black hole mergers. Gravitational waves travel at light speed. There are invisible forms of radiation traveling through space. Not very long ago, a particle was detected at the bottom of the Mediterranean Sea, off the coast of Sicily, at a depth of 3,500 meters, thanks to cables containing photomultipliers, which pass through and has as much energy as a ping pong ball thrown at high speed. It comes from another galaxy. A single particle, probably the neutrino, very light, which has as much energy as a ping pong ball, which contains billions upon billions of particles. So we don't know where it comes from, but we know that the physical phenomenon that produces this type of event is extremely violent, colossal. And this violence is hidden from us because our vision is limited to a narrow range of light frequencies, which masks many phenomena, which are real but invisible. Imagine if Aristotle or Plato had our detectors. Greek thought wouldn't be the same.
It would have been very different. In any case, we'll put this book in the description for anyone who's interested in reading it. In any case, thank you, Étienne.
Thank you, it was a pleasure. And I wish a good day to the readers of Science NV. I wouldn't have become a physicist without Science NV.
And I wouldn't have made this podcast without your example. So actually, that brings things full circle.
Thank you.